inside a graph, but you can think to the web like a directed graph. And one of the data structure used to fetch item inside a graph or working a graph is the queue. A queue is just a data structure that almost all of the high-level language has its own implementation where you can put element and process in the order. In this case, we are using a first in, first out queue. So yeah, you can imagine the web like a web graph, and a web crawler is a software that is able to work a graph. Again, a very, very high level and generic infrastructural overview about a web crawler. There are three main components. One is where the business logic of downloading elements resides, and URL queues, and a storage that might be everything. Every time a page is downloaded, all of the URLs inside the page will be enqueued into the queue, and then the text and the data inside the page might be stored somewhere. So, why you should roll your own web crawler? Well, motivation can be varied. First of all, web crawler used by search engines like Googlebot or Bingbot, I don't know if the name is exactly, are general purpose web crawler. They crawl the web for a very, very general audience. They have their own algorithm about page ranking. Maybe they crawl the data using some internal choice on how often a document should be crawled or how often a document should be refreshed. If you know where the data of your interest is, maybe it's time to roll your own web crawler because you can move from a very generic and general purpose web crawler to a focus crawler. It means that it can be more accurate. You can focus your power, let's say your infrastructure, to crawl only certain topic, can be highly selective, and of course the data that you are going to fetch from the web, maybe the final usage is not just for feeding a search engine. Let's say the data can be used for sentiment analysis, for recommendation engine. There are very, very different ways to use the data. Maybe because you are interested in benchmarking your brand, check the health of your brand or compare it against your competitor, measure the impact of a marketing campaign, and all of this data can be found on Twitter or forum or inside some blogs where people might tend to talk about your brand. The data you get from the source can be also used in finance. Maybe you're interested in building some stock market forecasting, risk management, price comparator, and so on. All of the data that you can get from the source of your interest can be then used into some pretty cool technology, like Hadoop, which is the technology where the MapReduce service of Amazon has been built on top. Then if you have the data, then you can program your MapReduce to do some cool analysis, or you can also, using some startup that like Wise.io, actually they are in private beta, that are offering machine learning, sentiment analysis as a service. To use all of these cool technologies, for sure what you really need is the data. Because without data, of course, you can't use this kind of technology. And last but not least, you may want to write your own web crawler for fun and profit, because it seems like it's a must-have a slide like this. So behind all of this motivation, I started to write my own web crawler named Polypus, because octopus was taken a name, unfortunately. And so when I started to write Polypus, actually it's now available on GitHub as open source project. The code now available is a slightly modified version of the code we are currently using in our production environment. When I started to write my web crawler, I had two main topics in my mind. One, that should be distributed and scalable, and second, it should be easy to use. My work has been very heavily inspired to Anemone. Anemone is another open source web crawler. Last commit I saw on GitHub was more than 1 year ago, so I'm not sure if the project is dead or is still maintained. But I like the idea behind Anemone because it was well designed, easy to use, but unfortunately it was non-distributed and not scalable. All of the information was taken in memory, so every time, you have just one single process, and if the Anemone crashes at some point, it's almost impossible to recover the crawling. So here, the polypus in action. This is a code snippet where actually it's taken from a real-life example. This is my own real-life example. I don't know if you ever had a chance to find an apartment in San Francisco, but it's one of the most difficult tasks to accomplish. So yeah, I started to scrape Craigslist, which is a famous site where you can find apartment, and then I saved all of the page on my local PC, and then so actually I built a kind of recommendation engine for just my own purpose. But this is just to tell you how it is to work with Polypus. You start with a seed URL. This is your starting point. And here, using a DSL-ish infrastructure, you can focus your crawler only on URLs of your interest. All of your URLs matching that pattern will be fold. And you can decide or storing the page somewhere or just processing the page in place. A page object would be passed to this Ruby block. Every page object has a method where it contains a doc. A doc is an object, is an instance of Nokogiri. I don't know if you know what Nokogiri is. Nokogiri is a pretty cool gem which is used to parse document, XML and HTML document. You can parse by using CSS selector like you do in jQuery, or you can even use XPath query. So yeah, this is how it is to use. So let's see what are the main components and see Polypus under the hood. One of the main components used by Polypus is Redis. What is Redis? Well, Redis is many things. Redis is listed as NoSQL database. Redis might be used as advanced key value store. Can be used as a caching server. Yes, it's a lot of things. In this topic, I would like to define Redis a way to share memory over TCP/IP. It means that you can use the internal data structure and you can model your Ruby object around an already ready-to-use data structure, and you can share those data structure between different processes, even different languages. Just to give you an example. List, which is actually a linked list, might be modeled around a queue object in Ruby. There is a hash. Actually, this is the hash of Ruby, set, sorted set, and so on. I'm almost sure that every high-level language has its own implementation of this kind of data structure. Even PHP, I think. No, I'm not sure about PHP. But. OK, and how Redis is used on Polypus. Redis is used a reliable and distributed queue. As I told you before in the very first slide, one of the main components of web crawler is a queue where you have to store URLs that should be sooner or later visited. How to distribute and make a web crawler scalable? First of all, you have to share this queue. Redis is very easy to use in this field and can help a lot. The pattern between behind the reliable distributed queue is just that a producer pushes an URL to visit into the queue. The underlying Redis command is rpush, and the consumer fetches the URL and at the same time push into a process list. All of these operations are atomic. It means that when a producer pops an element from the URL queue, at the very same time, the same element is stored into a processing queue. This happens at the very, very first time, same time, sorry. So if your crawler is going to crash or there may be some network failure, you don't have really lost the message because the message is still inside the processing queue. If the message has been successfully processed, it will be removed from the processing queue. Another process may be monitor the processing queue. If the processing queue is growing too much, it means that something is going wrong, but still you can pull all of the messages that has not been processed and re-enqueue all of the messages into the main queue. Since this pattern is pretty cool and pretty easy to use, it can be also used in our context. From the main code, I extracted a gem, so there is also a gem so that you can use a distributed queue also in our context. Again, Redis is also used as where tracker. At some point, you should decide if an URL has been already visited or is about to be visited. There are many different ways to implement this logic. One of them is to use a set. A set is just a data structure where you can insert element. For the nature of the set, only unique elements are allowed. And of course, Redis implements its own set. But when you think in a big data way, if you are going to crawl a very, very large website, you should expect that the memory occupied by the set will grow very, very fast. So my choice was to use a Bloom filter. So someone knows what a Bloom filter is? Okay. This is exactly what Wikipedia says. Bloom filter is a very space-efficient way for storing element in a structure and test whether this element is a part of the set. So it really used to test if an element has been already inserted into a set. There is no way to recover the original object previously inserted into the Bloom filter because this is about the Bloom filter algorithm. The object will be hashed for saving space, and you can just and only test if an element exists. If you're wondering where the Bloom filter is used in real life, I can tell you that Google Big Data and Apache Cassandra use a Bloom filter before to fetch a document and hit in the disk. They use the Bloom filter to determine if an element exists. If the Bloom filter say yes, so the expensive operation in fetching the document will be done, otherwise no. Web Chrome, the browser, has an internal Bloom filter that is queried every time you type an URL. It's used to identify if an URL that you are about to visit is a malicious one or not. If the Bloom filter says yes, at that point, an internal RPC query through the Google web server, whatever, will be done to be sure that URL is really, really malicious. Also, Bitcoin uses a Bloom filter to verify payment without running the full network node. Yeah, Bloom filter is widely used. It's very easy to implement as an algorithm. It's very powerful. But everything has a cost. Even if Bloom filters are very space efficient, this is a real life example. 1 million of elements are about 2 megabytes on Redis, which is very, very cheap in terms of consuming. This is a probabilistic algorithm. It means that for his nature, false positive retrieval are possible. It means that sometime, this is because of hash collision, it might say, yes, this element is a part of the set, even if not. But again, in a a point of view of crawling millions of pages, let's say every day, having a very way to saving memory and the RAM, because maybe you know that one of the most difficult resources to scale, even if in an environment like Amazon, is the RAM. RAM is still very expensive, it's difficult to scale. It is something that is not like adding a 1 terabyte over disk. RAM is really expensive. So what happened? Every 1 million of page, there is the 0.1% that some URL will be tested as, yes, this URL has been already visited, even if not. But I think this is a good trade-off in order to saving memory. Also, since the Bloom filter can be used for any other kind of topic, there is a gem that you can use also. If you have the luck to use the last version of Redis, let's say 2.6, I think, there is a support for internal scripting where Lua code can be run on the server. And my implementation is basically pushing Lua code over the Redis protocol, and the Lua code will be executed on Redis. It's a very, very fast, and it works very, very well. Another core component of my web crawler is MongoDB. Actually, it's not really needed. I mean, this is just if you need to store data and pages somewhere, you might decide to process pages in place instead of saving data. And MongoDB, in this case, is used just for storing page. Every page will be stored using the upsert command. The upsert command is just like if a document is already there, then overwrite, otherwise create a new one. By default, the body of the page will be compressed in order to save some space. There is no need to use the query because of the Bloom filter. So we don't need to check on Mongo if a page has been already stored or we need to store a new one. Yeah, of course, you can also decide to don't use Mongo at all by processing pages in place, but I would suggest you to store page because hitting the network and downloading the page is a very expensive operation in terms of resources, in terms of time. So if you start to process the just downloaded page in place at the very first time, later maybe you realize that the data you're going to extract is not complete. Maybe you need to refine your algorithm. So if you have the pages already stored, you can just rerun the process part of your code. Otherwise, of course, you have to re-download all of the data. This is the Polypus infrastructure. You can have an army of crawlers. All of the crawlers are orchestrated by a queue based on Redis, and the page adapter, the page storage adapter is based by default on Mongo. It can be really easy to extend Polypus by creating your own page adapter. You can think to store pages on S3, or you can think to store page on the disk, even if I would say it's not really the right choice. Yes, you can write your own adapter. You can even store pages on MySQL. But be aware that you should expect a very high frequency on write. So, is it so easy? Well, not really. Because Redis is an in-memory database. It means that every operation are done in memory. If I'm not wrong, starting from the version 2.2, the virtual memory option has been deprecated and removed. So it means that really every operation will be done in memory. Even if Redis can dump its content on the disk for a recovery in case of you stop and restart Redis, you will not expect that if your instance has just 2 GB available of memory, at some point Redis will be smart enough to start to swap or using your disk to doing some operation. It will not, because Redis has not been designed to work out of the RAM. In this context, a queue of URLs can grow very, very fast. I will say, just for my very personal experience, you should consider every one page about I would say 50 URLs per page. So if you expect that you're going to crawl 10 pages, you should expect 10 by 50 elements into the queue. A queue of 1 million of URLs is about 370 megabytes. Each element is about 400 char length. If you're wondering why an URL is so long, actually what I store in Redis is not just an URL, it's a data structure where there are also other information like the referrer of the original page, the deep, because maybe you can configure your crawler to stop to crawl a website if a certain level of the graph has been reached. And all of this data is wrapped around a JSON payload. So yeah, each element is about 400 chars length. Also keep in mind that for how Mongo is designed, MongoDB will eat your disk space pretty soon. Just for give you an example, 50 million of saved page are around 400 gigabytes. This is what I would like to suggest to you as a Redis configuration. You should use the max memory directive, 2.5 giga or whatever, and max memory policy set to no eviction. What no eviction does it mean? Redis has different type to handle max memory limit reached when these things happen. By default, it will try to remove keys that are about to be expired. So if you have a caching system, it's great to use the default configuration, because when you are really near to finish the memory inside Redis, using the default policy, it's just by removing keys that are about to expire. This is the typical use case in a caching system. But in our case, we don't have any keys with an expired time, because the queue should be persistent, the Bloom filter has to be persistent. So setting max memory policy no eviction means when the max memory limit is reached, stop to accept the write command and just reply with errors. It means that most probably your crawler will die, which is okay, shit happened, but as at least the queue and the current state of your crawler will be saved into Redis, because Redis can, of course, dump its content into using a separated process into the disk. At that point, you can resize your instance, migrate data, and so on. But at least you're not going to lose any data. So this is an experiment I did a few days ago using the current available code on GitHub. I used 6 T1 micro instances. If you know about Amazon, you should know that T1 micro is the smaller instance you can buy on Amazon. I don't remember the metric, but a micro instance is very micro with a very small CPU and very few RAM available. All these instances are dedicated to run the web crawlers. Each web crawler has been configured to work with 5 threads. And as a storage, I used the M1 medium instance, where I installed Redis and MongoDB. MongoDB with the default setting was just RPM install MongoDB, and the Redis with the setting I showed you before. In 24 hours, more than 4 million of pages has been downloaded, almost 5 million, which is pretty cool. Then I ran out of disk. Yeah. So, of course, I'm planning to enhance the crawler by adding new feature. On top of my mind, there is a Redis memory guard, because sooner or later, your very first bottleneck will be Redis if you don't have a way to keep under control the size of the queue. So actually, in production, we have something that works exactly in this way. We have something that can check the size of the queue, and if the size of the queue is going to grow too much, there is just enough loader that keep elements from the main queue and offload all of the elements into MongoDB. At some point, when the size of the queue it's okay for the dimension of your RAM, this component will move back element from MongoDB to the main queue. Then another feature I would like to add is to honor the robot.txt file, so that if somewhere else is listed as disallow, you can avoid to download where else with the disallow directive insert. And this is something which should be very, very useful, add support for Ruby Mechanize. I don't know if you know what Mechanize is a gem that has been built on top Nokojiri, if I'm not wrong, has been written by the same author. Is a DSL way to interact with a web page. With Mechanize, you can find form using XPath or CSS, fill the form, submit using post form, you can keep active the session. Why this should be really, really important in a web crawler? Because, you know, a website is not just plain HTML. A website may be a forum behind a login form. A website or information that you need can be displayed only if a search has been issued into a form, and adding this support maybe help you to keep the current login active and interact with a website like a human. And yes, if you are interested in this project, please fork and send me pull request, ask me for what you think should be added into the project. And yes, this is more like what I have to say about this topic. Questions?
Hi, what you save in MongoDB is just the raw page, or you can do some sort of work on it?
Okay. Okay, MongoDB is a NoSQL database that is a document-based database. It means that it's really easy to store document. In MongoDB case, documents are JSON payload. A page stored in Mongo means there is the body, which is compressed by default, and the deep where this page has been found, when, and its original referrer. This is something, in our use case, very useful to understand the graph, because we are really interested where the page has been fetched, when, and which was the path. Yes, because having the deep, you can also calculate something that is called the shortest path. That might be useful later for analysis. But yes, of course, the page adapter is not intended to be used as something to query. It's more really like a way to easily store pages. And since MongoDB writes in a very, very fast way, it was a good choice.
Base your solution on?
No, well, I checked inside Anemone because I really liked the way how Anemone was written, how its DSL implementation was done, but was absolutely pointless to use my use case because it's not distributed. It's just it uses just standard structure that are in memory. So if it crashes or you stop your crawler, there is no way to recover the previous work.
Okay. And if I wanted to avoid some URLs, how could I
Yes, sure, of course. You have two directives so far. You can specify the URL to follow, or you can specify don't follow links like that.
Okay.
So,
Regex is right. Regex. Okay.
yeah.